Ma'am, good afternoon, ma'am. Let me start the session, ma'am.
Yes, sir. We can start.
Okay, ma'am. Very good afternoon, participants. I like to welcome all the participants for a day 10 session 2 of AICTE sponsored 2 weeks online faculty development program on emerging trends and challenges in VLSI mixed signal processing for fourth industrial revolution. Welcome you all. It's my pleasure to welcome our today's resource person, Y. Uma Maheshwari, Manager Technology, Pramura Software Private Limited, Coimbatore. Welcome you, ma'am.
Thank you, sir. Thank you for inviting me for this session, sir.
Thank you. Before going to session, let me see the short intro about our research person. She completed her BE in Electrical and Electronics Engineering in Amrita Institute of Technology, Coimbatore, and completed her ME in Embedded System and Technologies in Anna University, and pursuing her part-time PhD in area of EMI filter design. She has a 20 years of experiences in the industry field with the various country clients like USA, Japan, Europe, and so on. Her main area of interest are like high-speed PCB design, post-processing of PCB design, process improvement, cross-functional analysis, customer relationship. She published more than 10 technical articles in a referred national and international journals and published the book in the title of Power Electronics with MATLAB and Simulation Tools for Electronic Systems, written book in the title Electrical Machines with MATLAB. She conducted one credit course for a UG and PS students in the area of PCB design system and EMI mitigation methods, and a certified Japanese language proficiency test JLPT entry certificate holder, and conducted courses for students and industrial persons for Japanese language. She is one of a Japanese language translator for technical documents and acted as a keynote speaker in various national and international workshops, conferences, seminars, and so on. In this way, I'd like to hand over the session to our resource person. Please, ma'am.
Hope my screen is visible.
Yes, ma'am. Visible, ma'am.
Thank you, sir. Thank you. So before going to the presentation, I would like to thank Kongunadu Engineering College organizers and other supporters for me inviting this podium. And so my area of expertise and area of interest is related to the PCB and EMI related fields. So today I was asked to do a EDA tool demo. EDA tool in the sense electronic design automation tool demo in terms of PCB. So printed circuit PCB is actually called a printed circuit board, which can be seen, which can be installed in every electronic products which we use. So for if you take any projects or any student project or research project, there will be definitely a printed circuit board which will be sitting on inside the module or system or product. So it has to be designed. First we need to have some idea. I think some of the persons have not yet muted. Organizers, can you ask others to mute? Karthik sir? Karthik sir?
Yes, ma'am.
Sir, I think there is some noise in this. Some of the people doesn't mute their.
Okay, ma'am. I muted
Please.
them, ma'am.
Yeah. Okay.
You can
Thank you.
continue, ma'am. Thank
Continue.
you.
Yeah. So as we discussed, so any electronic products, if you take, there will be a printed circuit board. So designing of printed circuit board is not in the curriculum as such. So it is actually as an electrical or electronics engineers, communication engineers, we should know how to design the PCB. We have some ideas, we have the concept, and it has to be translated into the product, right? So that product definitely should have the printed circuit board in it. So that can be designed or drafted in EDA, in the help of EDA tools. So in case of if you take any high speed products like mobile phones or laptop motherboards, there will be a complex circuit involved in it. So that has to be definitely has to be designed in the very much powerful EDA tools. Uh, Otherwise, you will not get the expected output or performance in it. So we'll see some of the basics of with the given time. Actually, 2 hours, I could cover the basics of the PCBs, and I will take a simple circuit and that we can design simple circuit in the EDA tool, and how we can do the manufacture of this simple circuit. So that we'll see with the given 2 hours. Actually, I may require at least 2 days to give the complete idea of this design flow. So with the 2 hours, I will take only the gist of the design process involved in the circuit. Okay, so let us first see what are all the components or what are all the terminologies involved in the circuit design, and after subsequently we can see how the design process goes, and we'll see after that we'll see the demo in that one particular tool that I'll explain in later. So for this introduction presentation, I have this agenda like what is PCB, what is the parts of the PCB, what are the parts of the PCBs, and what is units, and what are some design considerations to be considered as a design engineer, and what are the standards normally used for designing the PCBs. So as we said, a PCB is a printed circuit board. In a complex PCB, complex circuit, we have definitely need to have this a printed circuit board. So it is a thin board which can be in the, with the various materials depending upon the temperature, withstanding capability of the circuit. So we can use a fiberglass or a FR4 epoxy. So most of the materials are related to the application oriented. So we have to choose a board material so such that that application should suit the performance. And so so in the PCB you can see various types of components involved, and those components can be interconnected through the through the copper wires, like it is so called traces. So so we'll see the each and individual parts of the PCBs. First is a component. So component, as we know, there will be the two types of components: the surface mount components, where you don't have to drill the PCB, you can just paste on the PCB itself. The second type of components is a common conventional thing, that is that component will have the leads in it. So that leads can be inserted on the PCB, and it can be soldered through the lead or whatever materials we have. And so that's what we discussed. And what is the major difference between those two components, that is through hole components and surface mount components? So through hole components will consume area, and surface mount components will be very smaller with the same capacity. And one more major advantages of the surface mount component is not only the space constraint, it improves the signal integrity of the signal which we apply. In case of the high speed applications like mobile phones or any other communication application boards, definitely we will have surface mount technology components where you don't have to drill the component. So because of, if you drill the component, there's loss of the signal integrity happens. So in such case we'll have the surface mount components. So these in case of electromagnetic interference also, it solves some of the major noise values. So apart from that, as I said, the functionality of the surface mount components in case of FPGAs or other high-end controller or processor, there will be definitely latest techniques which applies for the packaging like surface mount package. So it has the more advantage over the conventional through hole components. So let us proceed for the next thing. So there will be, so various packages are available related to the component, so that will skip as of now. And in the PCB there will be 2-3 types of holes, that is for the either for the component insertion or the making the connections between the components. We'll use this vias. Vias is nothing but holes which is drilled on the PCB. For example, in the first this hole fill insulator, that is this is actually called the through hole. From the top to bottom, it is through process, the connectivity process happens. So the second process is, vias is called, that is holes is called. You cannot call this as hole, it is called as a via, that is vertical interconnect access. So it connects only between the top layer and the subsequent layer. So next is the buried via. Buried via will not have the access to the top and bottom layer. Instead, it has the connectivity in between the layers. So that is called buried via. So these vias are used for signal integrity purpose or performance improvement purpose, as well as the to make the floor for the connectivity, that is for copper wire tracing. So if we use these blind and buried vias, we'll have the more space rather than the through hole vias. So next part of this is pads. So pads means that it is nothing but a copper pattern, that is copper surface or copper shape, where the in which the components can be inserted, and we can take the connections out of these locations. So this is called pads. So these pads, definitely all the components will have the pads in a PCB. So that can be the shape with the round or rectangular or square commonly. So traces, the next part is the traces. Traces is called connection between two pads. So it is equivalent to the wire which is connected externally. So in between the components, you have the connections. You can take this as a trace. So this is you can equivalent this as a wire in the external thing. And traces sometimes connect to the vias or the pads. So this process is called routing. So routing or routing, whatever it may be. So the traces, making the traces is called routing. And we have to keep the traces as short as possible. So we trace length, that is connectivity length, should be very less in case of high speed designs. Otherwise you will have the delay in terms of nanoseconds. It will measure the delay, so that will create an impact in the performance of the circuit or system. And they're making the connections, we have some of the standards in it. So we need to have 45-degree angle. Acute angle should not be used. There should be smooth signal flow. So that tracing of the signals has to be drawn perfectly for the perfect signal integrity. And before making the traces, we should have the connectivity between the components. That is, we should know the connection of the actual circuit components. So in this case, you can see the green line. So this component is connected between this connector and other connector. So these rubber band lines are called rats. So with the help of the EDA tool, we'll have this. We can have this rubber band lines, that is rat's nest, and I'll show you how the rat's nest is coming from in the EDA tool. So then you will understand better. So as I said, the routing has to be done in the 45-degree angle. That is one between the traces should be 135-degree, and the other side, that opposite angle will be the 45-degree. So totally, you have to maintain the angle. Acute angle should not be there in as indicates in the right side. The right side is a bad routing in picture. And some of the terminologies involved in the traces are, we used to have the trace width. So width of the trace is actually a copper pattern, and the width has to be maintained according to the signal or ground. If you are taking the ground trace, or if you are taking the power trace plus 5 volt or 1 volt, whatever it may be, so the trace width plays a major roles in the PCB. So you cannot draw a trace with any kind of width. So the trace width has to be maintained depending upon the signal level which you transmit. And some other terms are trace to pad distance. So there should be some minimum distance has to be, because both the pad and the trace are copper. So in order to avoid the crosstalk or the short conditions, we have to maintain some of the distance between those copper patterns. So these values has to be entered in the EDA tool. And after that, this actually calls a pad. Inside the pad, you can see the drill size. So pad is otherwise called land or pad, so whatever it may be. So this is a hole size or drill size, which is in the case of through hole components. So pad to pad distance also has to be maintained. So this is one of the terminologies we use for the while routing the PCB. And also the track to track or trace, both are same. So track to track distance also has to be maintained, and this value, this design rule has to be set in the EDA tool. And this is called NPTH, that is non-painted through hole. This is nothing but a hole which can be used only for mounting purpose, mounting with another module or another hosting purpose. So next part is the vias. Vias is nothing but pads that is same as a copper pattern, which can be round in shape. And as we saw already, there are three main types of vias, that is through hole, blind vias, and buried vias. This is mainly used for connecting the signals between the components. So you can see how the connections happens between the vias is if you drill the PCB, the walls of the PCB will be plated. So you can see the capture pads, that is pads which with the copper pattern, and as well as the copper pattern, we have to plate the walls of the PCB, walls of the holes, in order to get the connectivity from the top to bottom layer. So another main concept of the PCB is the layer. So you can see you can see if you take a PCB, you cannot determine how many layers inside the PCB. So based on your complexity of the circuit, or based on the board size constraints, the layer can be varied. So if you don't have any constraints of the board size, you can do very well in the single layer itself. If you have the constraints in the board size, say for example, in the mobile phone, you have to have some 4-inch or 5 within the 5-inch level. So in such case, you have to have the PCB within the 3-inch or 4-inch. In such case, you have to have the lesser board size with higher number of layers. So layer means, so instead of drawing the circuit in one particular layer, you are splitting into the circuit into many layers. So you can see you have the top metal layer and bottom metal layer and internal layers. So these three are the conductive layers which we normally use in the multi-layer PCBs. So top metal layer is what you see in the top side of the PCB, and bottom layer is what you see in the bottom side of the PCB. So two-layer board consists of only top and bottom layer. Single layer board consists of only top layer. So multi-layer case, you have the internal layers which can be signal layer or power layer or ground layer. So for better signal integrity or noise reduction purpose, we use multiple grounds in between the signal layers. So if you take one signal layer, immediate next layer should be will be the ground layer for better return path of the current, and subsequent layer will be that can be a power or signal layer. So like that we arrange stack up of the PCB and give it for the production fabrication. So apart from these conductive layers, that is top metal layer, internal layer and bottom layer, there will be the another layer which is sitting on the top side. It's called a mask layer, which is used for masking purpose. It is a preventive layer. You can see some of the PCBs in green color or the bluish color. So that color indicates the mask. So mask is for purely for protection layer. And above that mask layer, you will have the silk layer, which is the purely text layer. That is non-conductive material, which is actually text layer. So you can represent whatever your logo or say for example, if you are using the connector, so you can mention the connector name in the PCB itself. So that in the silk layer you can have all the text related to the board. So similarly, after the bottom layer, that is subsequent to the bottom layer, there will be a bottom mask layer and the bottom silk layer. I will show quickly what is silk layer. So if you see this PCB, so the green color you see is actually a mask layer, which is top mask layer here, and the white color text you see here is a silk layer. So here also V plus, PG plus, DG. So these are all the silk layers. So which indicates the pads or component name clearly, which can be used for assembly or the troubleshooting purpose. So we should have the clear indication of the component, definitely. Otherwise, you will not know. The third person, if he sees it, he'll not know the what it is. So that is the purpose of the silk layer. And the mask layer is as we discussed, it is completely used for the protection purpose, because the copper reacts with the air. So we have to have the mask layer for. And some of the board materials concepts are, so actually one is the pre-peg and the cores and copper foils. So this I will show with the help of the picture. So you can see one here is a copper layer which is sandwiched, two copper layers which are sandwiched between the dielectric. That is, the dielectric material is a board material. Here you can see there are many board materials are available based on your board temperature testing capacity. You can select the board materials, that is the electric material. So this is the copper sheet. Two copper sheets are sandwiched between the board materials, and so this is complete setup is called core. And after the core, you have the pre-peg, and pre-peg is not actually some non-conductive material only. So it can be seated on this core, and after that you can have another copper layer. So this is the process we use for the multi-layer PCB. So here you can see the core consists of the board material with two sides copper clad, and pre-peg is a non-conductive material. And after upon that pre-peg material, you can have some copper. So this indicates a 4 layer. That is 1, 2, 3, 4. This 4 copper layers indicates a multi-layer PCB. That is 4-layer PCB. So this is another representation of the picture. So this is a cross section of the multi-layer PCB. So you can see the copper is masked. Here you can see the copper color. After masking, you can see the copper color. So that is purely for protection purpose. If you want to have this to be soldered in the top or bottom side, you have to have, you cannot clear the, I mean, you cannot cover this pad with the mask. Otherwise, you will not, you cannot, that lead will not fix to this copper. So you have to have them open. So only for non-access points of the PCB, top side PCB can be masked. So typical layer stack up can be signal layer, that is top layer, and the ground layer, and signal layer, ground layer. Then have the power layer, signal layer, and ground layer after the signal layer. So in between any signal, you have to have the ground layer for better integrity purpose. This is only for high speed frequency applications. So this via concepts, the connection between the vias. You can see this is a representation of skeleton representation of 4-layer PCB. If you have the pad on the top and bottom side, so we are plating the vias, that is holes of the PCB, and so from which if you're taking the connection from here to here, that is via to via. So if you access this point, the same current will be passing through it. So that is a concept while for the plating of the vias. So we use two types of units, that is imperial and English units or metric units. So metric units normally Asian countries, all Asian countries follows the metric units, and English units can be used in US and Europe markets. And so this is some of the conversion. There is 1 inch is equal to 25.4 micron. That is millimeter, and the mil and thou are the 1/1000th of the inch value. So these are all some of the units which normally used in the PCB design. And like everything, we have the standards, that is IPC defines the complete standards for related to the PCB, even for the board material or the flexible PCB materials, or the routing pattern or component creation. For everything, the IPC defines the standard for the related to the PCB process involved, including the assembly level. So these standards can be followed worldwide, and using these standards, all the designers will be aware of these standards and does the designs with the help of standards. So in case of local local PCBs, that is locally used PCBs, we don't need to follow the standards. So if you are selling the product, or if you are using the product in a professional way, it has to be undergone with the IPC standards. So there are three types of PCBs: class 1, class 2, class 3. So class 1 defines the general purpose electronic product, that is commercial cosmetic products, which that imperfections are not important in this case. So class 2 can be a dedicated product for the electronic designs, like communication equipment, instruments, military equipments, where there can be a certain cosmetic imperfections are allowed. So class 3 is a high reliability electronic products, which include definitely the military applications and other medical applications. So these three classes are defined in the IPC standards. And we saw different types of board types, that is single layer, double layer, multi-layer. So, and another classification of types can be rigid board, flex board, or rigid flex board. So this is called rigid boards. This can be a flex board with based on the applications and the board materials. You can play with the types of boards. And this is rigid flex. The partial portion of the connectivity can be flex material. That is, connections can be instead of giving the external connections, you can use the rigid flex combination board, which is in trend now. So this is stack up. It is in the EDA tool. You should have the flexible portions area stack up and the rigid portions in the stack up itself. So some of the EDA tools, high-end EDA tools supports this rigid flex board. So with this basic introduction to the PCB is completed, and I hope it is clear. If you have any doubts in this, we can have 1 or 2 minutes to discuss. Next, we are going to see the PCB design flow of the PCB designs. Hope it is clear. Okay, I shall proceed for the design flow. So in any EDA tool, in irrespective of the EDA tool, the process of the design can be like this, what we'll be discussing in subsequent slides. So the major EDA vendors are Cadence Design Systems, Mentor Graphics, Altium, Zuken. These are all the high-end players which is in the market. So these tools can have the ability to design the PCB and simulate the PCB with crosstalks and other noise, signal integrity and power integrity. So various options are available with these tools with the help of different bundles. So for this demo, I would like to introduce a Design Spark, which is an open source tool. So this slide shows actually the high-end EDA tools, which is very costly, and you might have in this your university or college. So apart from, if you are interested, if it is not there in your college, so you can use the open source EDA tool like Design Spark. So I personally use this for my evaluation, which is very equivalent to the high-end tools, but it has some limits even though, but it performs well in the for the case of designing the project, final year project or research projects. So simple PCBs can be designed using those Design Spark tool. So that I'll explain in the demo. I will show the tool demo after this presentation, after this small presentation. So in any tool, you have to have the logical design, physical design, and analysis purpose, analysis and verification. And the logical design will have the schematic capture, that is drawing the schematic the circuit of the concept, and the physical design will have the PCB layout, component placement, and routing. It can be manual or auto routing, and preparing for the manufacturers. And finally, it will have the simulate. It has to undergo for the verification as analysis. So there are many tools available. So concepts are available for getting the signal integrity analysis. So we'll see one by one later. So the first, logical design, you have to represent a component in terms of a logical symbol. So we have, before starting the PCB design, we have to have the library components creation. In that library component creation, you have, first thing has to be done is the creation of a symbol, that is logical representation of a component. So it will be like this. This is actually real component. So the real component can be represented logically like this. So the tool has to understand which pin and which pin and its functionality. So for that, we are creating a library component, one as symbol. So after creating the symbol, we have to create another actual representation of the component, that is called PCB footprint. So the footprint is actual size of the component which is going to be sit in the on the PCB. So after creating the PCB symbol and the footprint, we have to correlate these two, symbol and the footprint, in as a component. So totally, tool understands like this particular symbol has to be merged with the that is coordinated with the particular footprint. So the tool has to understand such a way that the particular symbol has to be same for the footprint. So we have to create a logical symbol and the footprint separately. So the both has to be coordinated with the component library. And another thing we can recently we can add can be a 3D model of a component. So any component can be component manufacturers will be releasing the 3D model as a step file, and the step file can be imported into the EDA tool. And at the end of the design, you can visually see the 3D view of the PCB, so that you can see if there are any touching of the component in case of the height or any other restrictions between the thing. So it will be very good to see in the 3D level, so 3D modeling level. So that will also I will show in this demo. And some of the major technical terms are involved should be considered in the while designing the PCBs are some of the electrical constraints, signal integrity constraints, and floor planning. So you cannot place all the components anywhere in the thing. So connector means it should be placed in proximity to the board edge. So like that, if you take any component, there will be some rules and regulations to be followed while doing the design. And the power issues, and RF. If it is a RF board, we have to have the clear idea about the RF signal, which is RF signal, what it does, and what is the frequency. All the things it has to be considered. If it is a mixed mode signals, we need to have what is the frequency of this signal to be sent, and what is the decibel levels which has to be followed for the EMI EMC protection. So all the things we need to consider before doing this design. So as we said earlier, the design flow like this: the schematic, layout, and actual board. So the schematic represents the circuit, what the concept of the circuit which you have has to be translated in the schematic capture editor. So there will be two editor. One is schematic capture editor, which is purely the logical representation of the circuit, and the next is this PCB layout editor, where the actual size of the components will be placing in the PCB layout editor, and which has to be translated to the actual board for manufacturing. So this is the total overall setup. And if you have any changes in the schematic, you can very well do it in the layout, or if you can do the changes in the layout, and you can transfer this layout changes to the schematic capture. So that annotation can be made easily with the help of the EDA tools. So I think we have seen enough about the schematic. Schematic is actually a logical representation of your circuit. So that is enough for the thing. So what does that schematic contains? If you are if you draw the schematic, the tool understands like which component has to be interlinked with the other pins. So for example, I have shown the netlist output. For example, A1 is a net name, that is signal name. If you take it is J1.11, U2.13, U11. So these are all the components. U1, J1 are all the components, and dot 11 is a pin number of the component. J1 pin number 11 of J1 is connected to pin number 13 of U2, and as well as the other subsequent pins. So this connection is called netlist. So this information is understand very well by the tool. So that is why we are making the connections. See, you can see here. So these connections, this pin number 1 of capacitor is connected to the op amp here. Its name is not visible here. So like this connection types is understand by the tool, and it is transferred to the layout editor. This editor which is shown here is a layout editor. So from the schematic editor, the layout editor, we have to transfer the schematic values here, netlist values, to the layout editor. So where you have the grids for working easily, so you can place the components on the grid. So you can change the grid value according to your convenience. So actual component value can be seen in the catalog of data sheet of the manufacturers, which release in the websites. So if you're taking any capacitor or any component, you can have with the help of the part number, you can search in the internet, that manufacturer site, you will get all the details, that is working conditions, working specifications of the PC of the component can be seen in the data sheet. Not only the specifications, you will have the physical dimensions of the PCB, so I mean the component, so that from the physical details only we are going to create the footprint of the component in the library. So as a gist, we have a schematic editor and have the PCB editor. So these both editors are used for designing the PCB. And apart from these two editors, we have the component library concept. So where we need to create a symbol of which to represent the logical representation, and we have to create a PCB footprint for actual components. So these two has to be correlated inside. I mean, these two has to be merged in the component library as a one component. So if you take 74LS00, you have two libraries, I mean two components. That is, one is for logical, one is for actual components. So these concepts library can be integrated with these two editors. So after creating the library, we have to create we have to draw the schematic in the editor, and the schematic edit from the schematic editor, netlist can be translated to the PCB editor, where we can place the components and do the routing and prepare the manufacturing files, that is final files to the production purpose. So this is the complete flow which is followed in the PCB design flow. So which is discussed already. So connections are nothing but nets, as we discussed. So before you start the layout, we have to have the clear understanding of the component which are using, and we need to collect the data sheets of the components which are going to use in the PCBs. And of course, we need to have the minimum and maximum size of the holes or mounting holes, and PCB trace with specifications. This can be get from the simulation of the PCBs, and minimum clearance levels you have to maintain. So that has to be defined before doing the PCB. And board size, this is a very important thing. So based on the board size only, you will have to play around with the layer count. So if you increase the layer count, the manufacturing cost will be increased. So we have to minimize the layer count with the given board size. And the limitations concerning the board shape, sometimes the board shape can be round or square or rectangle, or so depending upon you where you install your PCB is very important, so that the shape can be defined prior to the design. And the required file format can be Gerber. So this Gerber format can be it's a universal format which can be sent to the manufacturers for fabrication. So this is the physical design flow. So for any PCB, as we said, we need to set up the before. The previous slides explains what are all the constraints before you need to have this PCB. And this after keeping in mind those points, we have to set the environmental variables, the environmental setup in the EDA tool, and we have to do Am I audible, sir?
Yes, ma'am, it's audible, ma'am.
I think someone has muted me. Shall I proceed, sir?
Yes, ma'am, you can proceed, ma'am.
Yeah, okay. Thank you. So from the schematic editor, we need to translate the net into the PCB editor. So that when this screen shows the RADs, that is rubber band connections, that is netlist net information, that is connection information between the components is shown here. And after that, we need to arrange the components based on the frequency and the operation conditions. So we have to arrange the components such that there should not be any clash between the mixed mode signals and analog signals and digital signals. So we have to clearly segregate the components based on the requirement. So this is called the component placement. So after that, we have to create the power, and there may be various powers involved in the PCBs. So multiple. So instead of having one power plane in one layer, we can in a single layer itself we can have the multiple power. That is, power layer is actually a copper pattern which is connected to the related power. So for example, here it is 1.8 volt. So this pattern, like this is actually a skeleton shown here. So this is actually copper shape where all the pins here is related to the connected to the 1.8 volt. So similarly, here other apart from this pattern, so there will be another shape which is for 3.3 volt. So a single plane can have multiple copper pattern in it. So these are all used for the high-end applications. And for ground distribution, definitely we need to have the ground plane for the return signal. And for example, if you are taking the fine pitch components, fine pitch SMD components, we should take the fan out, like ground vias can be connected to the ground plane, and fan out has to be taken for taking the connections. And this is the routing of the boards. The top side and bottom side is shown here. So connections can be taken using the EDA tools, which can be a manual or automatic routing. So automatic routing have many limitations, like signal integrity. It will keep all the vias in order to complete the routing. So vias definitely have the inductance effect and the capacitance effect. So this will degrade the performance of the signal. So that we have to. It is better to have the manual routing. So I think we can skip. We can go for the PCB demo. And one more point, from the source to receiver, in the case of low frequency, the return path can be a direct minimal path. So it will take the minimal distance from the source receiver to the source. In case of high frequency, so the board will not, the return path will not have the minimal. So it will follow the exact path of the signal travels in the ground plane. So in case of in the case of driver to receiver, so if you are using the low frequency applications, if you have the low frequency applications, the current from the driver goes like this, and the return path can be the minimal shortest length between the driver and receiver. But if you take the high speed, this high frequency in terms of gigahertz, it will not follow the shortest path, but it will follow the same path of the current from the receiver to the driver. For that, we need to have the clear ground plane immediate to the signal layer. So in such case, if it is not a discontinued plane, I mean, if it is a continuous planes means continuous copper pattern which is present in the ground plane will not have the problem of this route. Otherwise, if the ground plane has the discontinuity in it, it will follow the longest path. So it will definitely create the electromagnetic interference noise, which is very, very dangerous, and it cannot have the electromagnetic compatibility levels too. So we have to, in the high frequency boards, we have to have the clear return path, that is current return path should be very, very clear. Otherwise, the displacement current will be high. And placing the signals have, we have to avoid the crosstalk between the signals. We have to place the traces between the, we should have some gaps to avoid the crosstalk. So there are another concept for, instead of using single-ended signals, you can to avoid the noise or to improve the signal integrity, there can be a differential pair signal routing. So where you can send the same signals in the negative and the positive directions, and the noise can couple each other. So when the gates cancel each other, so you'll get the better signal integrity level. So the same signal can be routed through the differential pair conditions instead of single-ended connections. And finally, after placing the components, after doing the routing, after doing the power and ground connections, we have to have the clear silk screen, which has to be placed legibly, and the user or the assembler has to understand the silk, so that it can be used for the assembly, or in case of troubleshooting, it is mandatory to have the legible silk. It can be yellow or white in color. And apart from that, another non-production layer, that is assembly layer, where you will have the assembling information of the top side or bottom side. So we can have the components placed in the top as well as the bottom side. So if both the layers are placed, we can have the top assembly layer as well as the bottom assembly layer. So assembly layer, they'll take the printout of the assembly layer sheet, and based on the instructions present in the assembly layer sheet, they'll do the assembling of the actual PCB. So next step is placing the solder mask. So the solder mask is definitely, as we discussed, it is only for the protection purpose. And finally, after completing all the process in the design flow, we'll do the checking. After that, we can create the output generation as a Gerber format. A Gerber format is a text file format, which is where you can have the XY information of and size information of a PCB layout parts, that is pads and traces. You will not have the complete intelligence about the component or the view of the component or other things. So it's just a text file that is in .gbr, which can be sent for the manufacturers, so that the component will, the manufacturers will not have the complete control over the your design concept. So you'll have some confidentiality in it. So with this, I close this presentation, and I'll directly go for the demo of the tool. Hope my screen is visible. If you have any doubts,
Yes, ma'am, visible, ma'am.
If you have any doubt till now in the concepts, I can explain now, or else I can go for the demo. I think I can proceed for the demo. So this is the screen which shows, if you open the Design Spark tool. So this is a Design Spark, which is an open source PCB design EDA tool. Design Spark, not only it releases the open source, it has the mechanical design software, and as well as electrical wiring design software. So there are many other softwares available in the Design Spark brand. So it is an open source tool. You can install by just simply logging, giving the login your details into this website, and by while opening you will see the windows like this. So for every project or any EDA tool, if you take, you have to create a project first. So first I'll create a project. So after the project, you can have the schematic design and the PCB design. So first I'll create a project. So in that project, I can create project file name. So then just press OK. It will create a project, and you will have some project window, which appears here. And after the project creation, you have to create the schematic design. And press OK. So in the project window, you can see the schematic is here. Schematic is present here. So if you double click the schematic, so you can see the schematic window appears here. So here you are going to do the schematic circuits drawing, that is schematic drawing. So before doing the schematic or layout, we have to create a library. So this by clicking the library, like you can see this icon shows the library. So this you can click here, and the design part has already default library components for various things. So for this, now I am going to take a schematic trigger like simple circuit. We'll create these components, and we'll see how this design creation happens. So for this, I need to create a new library. So even though this design part has the default library thing, so for this project, I am going to create a new library for specifically for this purpose alone, for this project alone. So see, the new schematic library is being created, and you can see there are no items in it. So similarly, for PCB symbols, you have to create new library. PCB library. So new library has been created. This is for this PCB symbols is for footprint creation. This schematic symbols is for schematic symbol creation. That is logical representation of a component. So for creating the component, I'll add one component now. So you can click the wizard. So wizard shows the number of processes to be followed. So if you just follow the simple instructions which is present here, so you can choose unit with the precision 3 digits, and types can be so for example, if you want to create in this as per this schematic trigger thing, so we need to create we have the resistor, capacitor, and the 555 timer. So 3 components has to be created. So first I'll create the resistor. So for the resistor, you have to have left side 1 pin and the right side 1 pin, right? So totally 2 pins component has to be created. So I select one of the topology here, and next, so pin styles you can have as it is, and pins on the left is 1, pins on the right is 1, and distance you can keep it like this as it is, because it's only a logical representation, so distance doesn't matter according to the actual thing. So symbol name we have to mention clearly. So just have this name for my reference. So this names also, there are some standards available according to the IPC. So just finish. So you can see one component is resistor component is added with 2 leads. One is from left and right, and so similarly you can use another. You can create another component like so this is we can create a 555 timer here. So I choose this all the side pin connections topology. So next you can have like this. So pins on left, I'll currently choose 555 timer has 8 pins, right? So pins on the left. This is a logical representation. So according to the circuit creation level, so you don't need to worry about the number of pins left and right. So for my convenience, I choose pins on left as 3, and pins on top can be 2. Pins on bottom can be 1. Okay, pins on right can be 2. So totally 2 plus 3, 5, 6, 7, 8 pins. So totally 8 pins I have created. So like my component will look like this. Symbol will look like this, and you can see timer. So finish. So you can see component has been added. So similarly, if you want to copy from another default library also, you can select. So for example, design part has the I want to copy this +5 power thing to my library. So if you can select, you can choose the design part. There is a default library which is used, which is installed in the while installation itself. So +5 supply I am going to copy from this library to my library. So copy to Kongu CH library. So just okay. So it has been copied. Similarly, I am going to copy the ground symbol. So I go to the default design spark library, and I can press G and D and copy to this library. So it has been added. And another component we need to create is capacitor, right? So the capacitors also can be created with the help of wizard, or you can copy from the design spark library. So currently we have some 4 or 5 symbols which can be used for this purpose. And so and after creating the schematic symbols, we need to create the actual footprint, actual component size symbols. For that, we can similarly for the wizard button will help us to create the components. So just press next and make sure the unit is your design unit. So here I choose mm with 3-digit precision. So here you have to choose the package. So for example, if I create a capacitor, so I use SMD components, a chip pack chip capacitor. So I just press next. So totally, definitely chip. If you choose the chip capacitor, the pins can be 2. And here you can see actual. You have for this only I told that the actual component data sheet has to be downloaded from the component manufacturer or vendor. So from those data sheet, that is a catalog, you will have these values. You have to interpret with according to the standard of the IPC. So here the E measurement is of everything is given. So so length is for the capacitor length I choose is 1.5 mm, and width can be T can be this oversize of the pads, so that will get take automatically. And height can be T and height H are same in this case, and the total distance can be say for example 3 mm. I am 3 mm. This 3 mm is not a correct thing, so we have to follow the data sheet which is mentioned in the can have 6. So the clear correct actual component size will be displayed in the data sheet of the capacitor manufacturers. So as of now I go with this default values, just random values. And next pad can be, see for example, if you want to make the first pin as a dot pad, or in case of ICs it can be useful. So I make this option disabled, and silk screen it will default in. So you can have the capacitor. So you see, the another capacitor or one component of the PCB actual symbol is getting added to this symbol. So similarly, I can create, I can copy the other components like timer and other things can be copied from the Design Spark or other libraries which is already present over here. So the timer has been already created, and this can be copied to so it has come here, and another capacitor has to be resistor has to be copied to our library. So now you have the capacitor, resistor, timer. So if you take other so you have the all other packages like QFP and BGA or PGA. So you have all the capability to create the footprints here. So right now I go with this our circuit. So we have, I think we have created all the components related to the particular circuit. So now we have done with the these two tabs. So here, the next important thing is we have to assign the components. So like here also you need to create a new library which is component library. Where you have to create, you have to correlate these two tabs. So for that we have to go for the wizard and press next. So here it is a part number. If you know the part number, you can this is for ordering the component purpose. So if you know the part number, you can enter, or it is optional values. And so if and the package type you have to select. So if first we'll select the capacitor value. So surface mode. So I select SM, and capacitor means it has to be start with the C. So I just press C for making the capacitor in the silk looks like C, and the component pins will be 2 pins. Number of gates is default is 1. So 2 pin component I'm going to create. So from and next, so you can see the flow where we have done that is, if you go to the details, so we'll have the capacitor and the details values, and next you have the schematic symbol where you have the capacitor. You can select we are going to create the capacitor, so you just select the capacitor, and next is a PCB symbol, and here the capacitor can be selected. So next is in this pin assignments, in this window you can see the pin assignments, like capacitor symbol of the pins can be assigned to the symbols of the PCB footprint. So assign 1 to 1. So this means that symbol 1 of the PCB schematic symbol is equivalent to the PCB symbol pin number 1 of the footprint. So that is the importance it has thing. So if you reassign the pins, you will get the wrong connection. So we have to give the proper assignments of the pins between the schematic symbol and the footprint symbol. So this has the main correlation between the symbol library and the schematic library, footprint library and the schematic. So we created another component. So you can see the previously you will see only the particular logical representation or the footprint representation. In this window, you can see when correlate with the schematic symbol as well as the footprint symbol. So here pin number 1 is equivalent to the pin number 1 of R. So that means this correlation. And you can create another component like, so actually it has we have given the wrong name, so we can rename this pin to capacitor. Okay, then you can create another name, another components like resistor. Resistor is not a surface mount component, so through hole component. So I just press through, and resistor can be referenced as R. So I just gave R, and component can be pin number of components can be 2, and default number of gates is 1. So next you can here you have to select the resistor, and next here also you have to select the resistor footprint. Next here 1 to 1 assignment. Then next, so resistor has been added in the component library, and similarly we have to create the timer. Is a SMD component, so I surface mount component. Timer, it is a IC, so I put U as a reference designator, and number of pins is actually 8. Number of gates is 1. So here you can select the symbol of schematic representation and with 555 timer, and select. Next, make sure you select the correct library. One to 1. So pin number 1 of the schematic can be the pin number 1 of the footprint. So all the components are getting added, and So from this, the library work is getting over. So you are going to place the schematic editor, right? So in the project window, you have the schematic. You have already created a schematic sheet, that is schematic window. So this tab shows the schematic of the thing, and we have to place the component. Like you can add the component, like add component, and you can see all the components are getting added. You can select the corresponding uh, 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 component from this window. So 555, just add capacitor, add. So I have the capacitor. Sorry. So you can see the capacitor is I have given the C value. So this automatically takes C1 and C2. So similarly, resistor R1 and R. So it will take incremental value of the count related to the count. And before that, we have to create another thing. So power supply. So we'll first arrange the component. So just you can rotate if you want to rotate the component by 180 degree, or you can place the values here. So just by clicking the component, you can move the uh, component anywhere in the sheet. So according to the sheet, you can according to your circuit, you can see. And if you want to make the connections between the pin number uh, uh, first pin to here, just press the thing. So it makes you can see the X mark is getting disabled from this. So similarly, if you want to short, double click the thing, you will get the short here. And likewise, so all the things can be done, all the connections can be done. So if you want to take the short here, you can short. So similarly, whatever you want to have, so all the functionalities can be done using those this add connections, or by just double clicking the thing. And you can see the property of the component by right clicking the properties. So you can see if you want to have any changes or any suggestions, you can see with the help of the property window, where you will get the complete details about the component. So here in the case of a resistor R1, its name is R1, component is package is through hole, component is resistor, and the symbol. So other details also will be present over here. So similarly, I have completed. I'll open the other completed project for the schematic trigger. So you can see the connections has been completed. So here So you can see the complete. I'll make another. I'll delete this project. Okay. So you have this schematic connection. So you have to. Here you have to create a new PCB design, and you can name this PCB design as schematic PCB. Okay, so where you will have you will get a new window which will ask for the informations of the PCB design details. So you can give unit as mm and three decimal precision. And next, what you want to have, this number of layer can be, you can select either it is a single layer or two layer or four layer PCB or whatever it may be. And you can press next. You will have the board size information. So by default it is 20 mm by 20 mm. So I can change by 20 mm by 10 mm or whatever it may be, according to your requirement. Okay, you will have this board layout. So from here we need to transfer the circuit to this board layout. So for that we have to use the tools translate to PCB. So again, if you want to change those values, you can change here itself, here also. So I select mm. So some of the warnings has been received because the signal net class was not defined. So these warnings can be, we have to correct in the schematic editor itself. So you can see the rubber band line here. So from here, so the timer is not transferred, as we can see why it is not received here. Okay. After receiving all these components here, I will check. We have to check the log file for the issue why it is not received here. And after checking all the components, we have to place the components inside the PCB. I mean, inside the board layout. Suppose if you have defined the wrong board layout, you can increase the board size, like expanding or stretching the thing, and we can have all the components can be placed inside the PCB. I mean, inside the board layout, like just by clicking the component and dragging it in it, dragging in it. And if you want to have, see, you can see the connection is reversed here. So the connection goes reversal. So you can rotate the component by 180 degree so that you will have the clear routing connections. So by clicking the copper that rubber band line, or you can use this add make connections or add track uh, functionality. Just by simple click it will have the thing. And similarly, you can have the all the connections can be routed using this trace connections. So So in the project window, you can see all the connections are getting open. I mean, all the schematic or the component PCBs are getting shown here. So I will show the completed board. So the completed board will look like this. So here all the components can be placed and routed, and after the things, you can have the reports. You can generate the reports. Before that, before generating the reports, you can set the design technology, that is design rules related to the board. Like you can have the track to track spacings, like 10 mm spacing should be required, so or 2 mm. So whatever your requirement be based on your PCB signal thickness, signal or functionality, you can set the values, and pad to pad distance can be set 2 mm or so this specifications has to be decided by the PCB designer. And similarly, all the things can be set, and like part style and other informations, everything has this window. So you can set the power line width also, power line or signal lines. So all the things can be set here, as well as the net capability, so +5 or ground. So in this case, we have used that +5 volt power or ground, and the spacing also can be set here, as I discussed earlier. So these rules can be set here, and after setting those values, applying those values, we can do the output, that is reports. So here you can take the bill of material, that is what are all the components which are used in the PCBs, that is used in the design, can be generated using this thing. So one capacitor, two capacitors, two resistors, and one timer. So these are all the components. So similarly, you will get all the information related to the thing after setting while and if you generate the dangling tracks, that is if your traces are not connected properly or it is open circuited, so you will have the dangling trace report. So totally one count here, it is shown at the C1 side. The dangling trace report is shown here. So you have to correct these values according to the circuit. So similarly, so we have the multiple reports can be taken out of this PCB and used for the thing. And finally, you have you can have the 3D view. If you want to have the 3D view, you can have the 3D. So by default, we have not imported any 3D step files into this PCB, but by default, it takes the 3D visibility. So in case of the component height, if you import the exact dimensions of the component, you'll get a clear idea whether it is going to touch this proximity component or not. So this is the 3D view of this component, I mean PCB. And you can change the color of the various entities present over here. So according to this, you can play around with the colors, and you can measure. You can use the measure tools to measure all the things, and you can check the PCB by doing design rule check. So this check can be based upon the settings which we give in the design technology tab. So it will check the track to spacing of track to tracks against the value set in the design technology tab. So this is the major this is the tool which can be used majorly before releasing the fabrication layer. So after checking only, we will be taking the manufacturing plots. So manufacturing plots will have the default layers which is present in the PCB set setup. And so you can select the either PDF or PDF can be, this is for viewing purpose. The Gerbers can be the Gerber can be selected for giving to the manufacturers, and you can run, you will get the .gbr text file. So that .gbr text files can be shared with the manufacturers for the production purpose. So for various auto placement components, auto net routing components, and so another, if you want to edit the component, you can in between you can edit the components and re-import, update the changes in the from the libraries, and optimize nets. So various other tools are available, and design calculators. It will calculate the trace with characteristics, impedance values. So there are various other concepts are available, like track impedance. So impedance has to be maintained throughout the board uniform, otherwise reflection current will have the voltage drop or power drop. So it will like affect the board performance, heat, signal integrity. So we, and also the heat sink we have to provide for the component which operates in high speed. And so various considerations has to be governed before designing the PCB. So just I showed the simple circuit, how to create the components and how to create the component libraries with the help of the library editors, and with the help of a schematic editor, or with the help of a schematic footprint layout editor. How we can create the PCB layout has been shown. So with this given time, I can show this much only. So if you have any clarifications, you can contact me or in the future also. So if you have any doubts, I can ready to answer here.
Dear participants, if you have any doubts or queries, you can ask. Ma'am, I think there is no queries from participant sides, ma'am.
Okay, sir.
Let me conclude the session, ma'am.
Yes, sir.
The roots of all goodness lie in the word of appreciation. In this way, I'd like to thank our today's resource person, Uma Maheshwari, Manager Technology, Pramura Software Private Limited, Coimbatore, for providing a wonderful session on the topic of PCB design demo in the EDA tool. Thank you so much, ma'am.
Thank you, sir. Thank you for inviting me this session.
Thank you, ma'am. Dear participants, the date and session to attendance and the feedback link is posted in chat box. It will be open up to 30 minutes only, so kindly fill it soon. And one more information to all the participants. Tomorrow is the last day of the FDP. So tomorrow at 3:30 p.m. we have a MCQ test. We will share the test link at during that time. Thank you all. Participants, the date and session to attendance and feedback link is posted in chat box. Kindly fill it soon. And one important information to all the participants. Tomorrow is the last day of this FTP. So regarding that, tomorrow at 3:30 p.m. we have a MCQ test via Google form. We will share the Google form at 3:30 p.m. tomorrow. Thank you all.